Do. Let's do this. Let's do this. Alright. Solutions tonight. Alright. Alright. Solutions. Alright, cool. So tonight we're doing solutions. So we're into the third quarter, and then after this, everything else after this video is fourth quarter chemistry topics. So we're almost done. We only got a few more of these left. So we got solutions, kinetics and equilibrium, acids and bases, organic chemistry, redox, nuclear, a couple more that I'm forgetting, but we're almost done. We're really close to being done. So let's get going. So what is a solution? So a solution is a homogeneous mixture. Meaning when you formed a solution, it's fully dissolved and pretty much every solution that you'll see in chem is mixed with water. So you'll see the abbreviation aqueous. You don't have to see aqueous. You can have mixtures. You can have homogeneous mixtures, uniform mixtures that are not mixed in water. But for the most part in chem, they're going to be aqueous, which means they're mixed with water. And when you have a solution, you have a solute, which is being dissolved, a solvent, which is what's dissolving, or the dissolver, and those come together to form a solution. So, for example, salt, a solvent, or a solute, plus water, your solvent. So salt is what's being dissolved. You're dissolving the salt in the water, which is the solvent. They won't chemically react. That salt is just going to mix with the water. So you get a solution. In this case, it's salt water. Now, it's important to note when you have an ionic compound. So an ionic compound, a metal and a nonmetal. So that's ionic. Like NaCl, which is salt. So when you take NaCl, that solid form of NaCl, and you dissolve it in water, they dissociate into their individual ions. So they dissociate into the negative chlorines and the positive NAs. So when you dissolve ionic compounds in water, they dissociate. You can do this with any ionic compound. So MgF2 as a solid, dissolve it in water, and you'll get your Mg, which on the pure is a charge of +2. And in this case, 2 Fs, because there's 2 of them, each charged -1. And they're both AQ. So solutions involve a substance completely dissolving in another substance. A solute completely dissolving in a solvent. Alright, you can have different types of solutions. You can have unsaturated, which means you can dissolve more solute. So let me write can dissolve. Can dissolve more solute. So In an unsaturated solution, you have only partially dissolved that substance. So, normally, you'll see questions involving saturated and unsaturated using table G, but we'll get there in a minute. Saturated is the max amount of your solute. So if you dissolve if you try to dissolve even a tiny milligram more than this maximum, it will not dissolve. You have reached the maximum amount. And then there's supersaturated. So supersaturated means you have more solute than normal. So usually at a certain amount, so let's say you had 10 grams of NaCl. Normally 10 grams of NaCl can be completely dissolved, I'm making these numbers up, in 20 grams of water. Well, if you increase the temperature of the water, but not the amount of the water, you can dissolve more NaCl than normal. So supersaturated is all temperature dependent. It depends on the temperature. And that's how they make those like rock candies. Not pop rocks, but that like crystal looking rock candy on a stick. They take a whole lot of sugar and they start dissolving it in water. And as they increase the temperature of the water, they can dissolve more sugar than normal. So it becomes supersaturated. And then when you cool that sugar down, when you cool the water down, the supersaturated sugar starts to recrystallize on that stick. And then you get that rock candy stuff. So, a lot of these you can, a lot of this using table G. So table G are all your solubility curves. And you just have to read these carefully. And we'll do just a couple of examples here. Let's take NH4Cl as an example. That curve right here. Actually, I'm just going to highlight it. Questions can be like, how much NH4Cl can be dissolved at 60 degrees if you are dissolving it in 100 grams of water? So, the y-axis is being dissolved in 100 grams of water. So all of these substances are being dissolved in 100 grams of water. For a saturated solution, you go all the way up until you hit the line and then just see how many grams you can dissolve. And I would approximate about 58. So NH4Cl, you can dissolve up to 58 grams. Anything above this line for NH4Cl, so anything in that red going up, will not dissolve, because that is over the point of saturation. So anything above at that temperature, anything above 60 degrees, anything above 58 grams at 60 degrees for NH4Cl will not dissolve. Anything below, so I'm just going to change the color to orange here, anything below where it hits the curve is unsaturated. Alright, so take any line at any given temperature. Where you hit the line is saturated. Above the line will not dissolve. It will just stay as that crystal. It will stay as a solid. Anything below the line is unsaturated. Okay, Sometimes other tricks they can play is they can change how much water you're dissolving it in. If they change it to 200 grams, just take everything on the y-axis and multiply it by 2. Solve the problem normally. So, what would it be worded like? It could say, how many grams of KNO3 can you dissolve in at 30 degrees in 200 grams of water? So, how much KNO3 can you dissolve? Here's KNO3. It wants to know what's the maximum amount you can dissolve, so where is it saturated? And normally, you would follow 30 degrees up, take this across, and I'm going to guesstimate that normally you can dissolve 45 grams. But it said it was 200 grams of water. So I have to multiply this by 2 and get 90 grams. Another question can be worded like, at 50 degrees, if you add 35 grams of KClO3, what amount will not dissolve? So normally, KClO3 is saturated at about grams. So you can dissolve 21 grams. If you add 35 grams of it, 14 grams of KClO3 won't dissolve because that's over the point of saturation. So again, this red area, up to 35, won't dissolve. It will stay as a solid compound. It can't dissolve above that saturation point. Another trick they might try to play is, instead of saying how much KNO3 can dissolve in 100 grams of water at 50 degrees, they might say 50 grams of water at whatever temperature. So if they change the amount of water from 100 to 50, take everything on the y-axis and just divide it by 2. So, if we were doing KNO3, which is this curve, and we said 50 degrees in, well, let me choose a different temperature just so it's not the same number. 40 degrees in 50 grams of water. So 40 degrees, you can dissolve up to right about there, which I'm going to guesstimate as about 64. So, if you're dissolving 64 grams in 100 grams of water, it's saturated. But since we changed the amount of water to 50 grams, we just divide that by 2 and get 32 grams instead. And that's basically the extent of the Table G stuff. I'm going to come back to Table G later to just go over another concept. But I just want to make sure we familiarize ourselves with Table G again. Alright, let's see what I want to talk about next. Alright, let's talk about the concept of like dissolves like. Meaning, molecules with similar polarities will mix. So, this is a question that they like to ask, and you can just word it like this. So if they ask, for example, in terms of molecular polarity, why does ethanol dissolve in water? You can say, well, water is polar, so therefore ethanol is also polar, because like dissolves like. Or if you have a little panic attack, or you forget, and you don't remember if water is polar or nonpolar, if the substances mix, they have similar molecular polarities. If they don't mix, sometimes they'll also word it like this. In terms of molecular polarity, why do oil and water not mix? Don't mix means they have different molecular polarities. So, I like to ask this question fairly often because it's about solutions and it's all about like dissolves like. Don't just say like dissolves like, because it will almost always say in terms of molecular polarities. The concept is similar polarity, mix. Different polarities don't mix. So polar and polar will mix. Nonpolar and nonpolar will mix. Polar and nonpolar will not mix. They will form a heterogeneous mixture, meaning separated layers. What else affects solubility? Well, if you increase the temperature, you increase the solubility. What does that mean? So, if you go to table G, and you look at pretty much every substance on table G, as temperature goes up, the amount you can dissolve will typically increase. However, there are 3 substances who decrease as temperature increases. And as you might correctly predict, these substances are gases. So, normally we would say temperature has a big effect on solubility, where increasing it typically increases the solubility. However, for a gas, to make a gas soluble, more soluble is lower temperatures and higher pressures. That is more soluble for a gas. And the analogy I usually give my students is think of any carbonated beverage. Carbonated beverages come in sealed containers, so sometimes it has a twist-off cap, or if they're in a can, they're in a closed container. So that keeps the pressure high, keeps the gas within the confines of the liquid that they're dissolved in. Because it's all carbonated beverages are just carbon dioxide dissolved in water. And where do most people keep their sodas or their other carbonated beverages like seltzer and stuff? Most people keep them in the refrigerator where it's cold to once again gas dissolved in the solution. Now, you want to be careful because you don't want to confuse this with what an ideal gas behavior is. So this has nothing to do with solutions, but ideal gas behavior is a bit different. That is the opposite. That is a high temperature and a low pressure. So a gas will remain dissolved in solution, cold temperatures, high pressures, but a gas will act more ideally at a high temperature and a low pressure. So try to keep those two straight. I know that's annoying because they're opposites and they both deal with the word gas, but just try to keep that in mind. The only other thing to keep in mind with pressure only affects gases. I always forget if it's A. Only affects gases. Pressure will not affect a solid, and pressure will not affect a liquid. Table F. How do you read Table F? So, Table F shows how soluble different things are when they're combined with different substances. So, everything in this group is soluble. So these will all form aqueous solutions. But everything here in these two are exceptions to being soluble. So everything here in these boxes are exceptions. So these form a solid, aka precipitate. Did I spell precipitate right? Yeah, that just looks weird. Anyway, what does that mean? So, when Ag, Pb, or Hg are combined with Cl, Br, or I, they will form an insoluble compound, which means it doesn't dissolve. So you'll see this a lot in a chemical reaction, and you'll see this most in a double replacement reaction. Let's say you're reacting AgNO3 with NaCl. Ag is a positive charge, NO3 is a negative, Na is a positive charge, Cl is a negative. When these react, the two positive charges switch places with each other. Now, according to my solubility rules, anything combined with a group 1 element or a nitrate, which is what I have in this reaction, are always soluble. There are no exceptions to their solubility. So these two substances at the beginning are both aqueous because they both dissolve in water. NaNO3 is a double combo, group 1 and its NO3, so that is definitely aqueous. But AgCl was one of the exceptions down here. When Ag is combined with Cl, it's not soluble. It forms a precipitate. It forms a solid whitish gray precipitate at the bottom of your test tube or flask. The other side of table F says that all of these compounds are insoluble going down. So everything on this left-hand side of the list forms your solid precipitate, where these exceptions will be aqueous. So let's do a couple of examples here. If you react lithium carbonate with magnesium chloride, you will get lithium chloride. Just trying to balance my equation here. You'll get lithium chloride and magnesium carbonate. If I go to table F, I see that carbonates are insoluble unless they're with group 1 or ammonium, group 1 or ammonium. Well, magnesium is in group 2. So since magnesium is in group 2, this is your solid precipitate. Another question you might see is like, which one of these compounds is soluble? And they'll give you a list like BAS, PBS, Na2S, whatever, Al2S3. So you'll notice the ion they have in common is sulfur. So if it asks you if that is soluble, I'm probably going to check table F. Sulfurs are insoluble unless they're with group 1 or ammonium. Well, that's in group 2. BA is in group 2. PB is in group like 12 or 12, something like that. AF group 13. Na is in group 1. This is soluble. So that's pretty much how you read table F. All right. Concentrated versus dilute. Dilute means you tend to have more water or more solvent compared to your solute. So if you're dissolving salt in a big gallon container of water and you just throw in a few sprinkles of that gallon of water will probably still taste like water. But concentrated means you dissolve a lot of solvent, of solute, in the solvent. So if you take that same gallon of water and just buy a big container of Morton salt and just pour it in there, it's going to be very concentrated. It's going to taste really salty, and that's going to be kind of gross. So we did a lab with this in my class with Kool-Aid, where we made some Kool-Aid and we tried it. And some of the Kool-Aid just kind of tasted like water, and then some of the Kool-Aid just tasted like you were eating sugar, and it was kind of gross. And some of my students liked it. That was weird. Anyway, that's concentrated versus dilute. How do we express concentration? So concentration we express using molarity, which will always be abbreviated with a large M, a capital M. And the formula for this is on the reference table. Where, if you just look for the word concentration, you will find molarity. And it is moles of solute per liter of solution. So moles per liter. So for example, if 60 grams of NaCl are dissolved in 200 milliliters of water, what is the molarity? Well, we got to do a couple things here. I have 60 grams of NaCl. I need to convert that to moles. I have 200 milliliters. I need to convert that to liters. So, let's do moles first. Moles equals given mass over gram formula, aka the periodic mass. And if 60 grams was given, and according to the periodic table, NaCl should weigh 23 from Na plus 35-ish from Cl. So that's 60 divided by 58, which is about 1. So I have about 1 mole of NaCl. 200 milliliters, if you divide that by 1,000, you will convert it to liters. So to convert from milliliters to liters, just simply divide it by 1,000. Now I have 1 divided by 1 mole divided by 0.2, and you can put that in your calculator, but this should be, if I did the math right in my head, 5 molarity. This has a concentration of 5. Let me make sure I did this right. I did. Okay. So, they could also give you molarity, like the molarity is 2 in 100 milliliters of solution. How many moles? Well, the molarity is 2. The moles you do not know. And if I divide that 100 by 1,000, I get 0.1 liters. Well, if you do 2 times 0.1, you should get 0.2 moles. And that's concentration. That's molarity. You can also express concentration in terms of parts per million. And most of my students, and many other students, tend to forget the million. So, this is mass of your solute per mass of solution times 1,000,000. So, if you had 5 grams of NaCl in 1,000 grams of solution, what is this in parts per million? Well, you do 5 grams, because NaCl is your solute. NaCl is what's being dissolved. Divide it by 1,000 grams of your solution times 1,000,000. And you can also abbreviate 1,000,000 as 10 to the 6th. So if you 5 divided by 1,000, you should get 0.005 times 1,000,000, and that should get it up to 5,000 ppm. They also sometimes will ask you to solve a problem given parts per million. So if 5 parts per million, a 2,000 gram solution, and I'm abbreviating these questions to make it quicker. Mass of solute, well, set that up. 5 parts per million is equal to some mass of solute divided by 2,000 times 1,000,000. Don't forget the times 1,000,000. Right here, I can multiply both sides by 2,000. So I multiply by 2,000. Cancel those out. Multiply this by 2,000. And now I have, what is that? 100,000? No. 10,000. Come on, Mr. G. 10,000 equals X times 1,000,000, which I'm just going to abbreviate as 10 to the 6th. Divide both sides by 1,000,000, and you should get X equal to 0.01 grams, or is it 0.1? Let me double check. 10,000 divided by 1,000,000, 0.01 grams. All right. So you got to be able to use the parts per million formula to solve for parts per million, or solve for grams of solute. You also need to be able to use the percent composition formula. And this one, this one on the Regents really tripped people up last year. That is mass of part divided by mass of whole times 100. So, if 20 Cl dissolved in 100 grams of water, what is the percent comp of NaCl? Too many students will do 20 divided by 100 times 100. It's mass of part over mass of whole. This is a part. This is a part. If I want the percent comp of NaCl in this solution, then it's 20 grams of NaCl divided by the whole, which is 120 grams times 100. And that should be a little less than 20%. So if I do 20 divided by 120, don't forget to multiply by 100, you should get 16.6%. When you see a question like this, or if you see a question like this, don't forget it's part over whole. Part over whole. You can also see this worded as a percent by volume, which will be the same thing. So if 50 milliliters of ethanol mix with 150 milliliters of water, what's the percent by volume of ethanol? So that's just asking for the percent composition of ethanol in this solution. If my milliliters is ethanol, then my solution is the whole, which is both the ethanol and the water mixed together. So I'm doing 50 divided by 200, and then multiplying that times 100. So 50 divided by 200 should be a quarter, times 100 would give you 25%. All right, colligative properties. Generally speaking, if you dissolve a solute in solvent, which again will typically be water, the freezing point will decrease and the boiling will increase. So this is why they spread salt on the roads in winter. Putting the salt and putting it mixed with the water will lower the freezing point of the water. So instead of the water freezing at 32 degrees Fahrenheit or 0 degrees Celsius, maybe it'll freeze at -2 degrees Celsius. So it brings that freezing point down, makes it more difficult for the water to freeze, makes it have to get colder for the water to freeze, so its freezing point decreases. Boiling point will do the opposite. If it's more difficult to boil, it's harder to get the water boiling, it's going to boil at a higher temperature. So, speaking, you dissolve a solute in a solvent, the freezing point goes down, and the boiling point goes up. If all the same type of substance, or the same, I'm going to say not type of substance, let's say the same solute, or all molecular solutes. When I say molecular solutes, I mean non-metal solutes. More moles equals lower freezing point, higher boiling point. So the more you dissolve, the lower the freezing point will go, and the higher the boiling point will go. So if you were to compare 0.1 moles, 1 mole, 10 moles of C6H12O6, this would lower the freezing point the most and raise the boiling point the most. The same is true for an ionic substance. If you were comparing 0.1, 1, and 10 moles of NaCl, they're all the same substance, they're all the same type of substance. 10 moles will lower the freezing point the most and raise the boiling point the most. So if they're all the same solute, or everything you're comparing is a molecular solute, meaning if you were doing, again, 0.1 moles and 1 mole of glucose and 0.1 moles and 1 mole of sucrose, which is, again, another sugar molecule, or let me do something I can write. Let's just say ammonia. Generally speaking, the one that's 1 mole is better. Will lower the freezing point more, raise the boiling point more. Now, ionic beats molecular if the same amount of moles. So if you were doing 1 mole of glucose again and 1 mole of NaCl, NaCl will win and lower the freezing point and raise the boiling point more than glucose. If you're comparing various ionic substances, more ions win. So if these are all 1 mole, NaCl is Na plus and Cl minus. MgCl2 is Mg2 plus with 2 Cl minus. AlCl3 is Al3 plus with 3 Cl minus. 1 Al, 3 Cls, this wins. Lowers the freezing point the most, raises the boiling point the most. Now, some of you might be like, wait a minute, H12O6, doesn't that have like 24 ions? C6H12O6 is all nonmetals, which means it has no ions, which means it just stays as C6H12O6 when you dissolve it. So molecular substances, when you dissolve them in water, take solid sugar and put it in H2O, they don't dissociate. They just mix and form a solution. There is no dissociating occurring with a molecular substance, aka any substance that is nothing but nonmetals. That's it. So, I will get this video and the video from yesterday with practice problems uploaded to my teacher site tomorrow. Hope you all have a great night. If any of my students tuned in for my 3rd block, don't forget that you have a quest tomorrow. I hope you guys have a great day.